Okay, this Google Hangout is live. We are here today with Dr. Edward Thomas Jr. He's a professor at Auburn University. He has his BS in physics from Florida Institute of Technology. He got his master's in physics at MIT and his PhD in physics at Auburn University. He is a full professor now at Auburn University and is the inaugural Lawrence C. Witt Professor in the College of Natural Sciences and Mathematics at Auburn University. This seminar series is supported by a grant from the University of Central Arkansas's Foundation and with support from the Society of Physics Students and the Department of Physics and Astronomy here at UCA. So we want to welcome Dr. Thomas to our Google Hangout and our guests there in Boston at Suffolk University. Take it away, Dr. Thomas.
Okay, great. Well, first of all, thank you very much for taking your time chatting with me here. And I'm going to, I get a little bit of feedback, but hopefully that's not too bad on your end.
It sounds great on our end.
Okay, great. So I'm going to start the presentation, and I'm going to, as Will said, I'm plasma physicist. And I study a particular type of plasma known as a complex or a dusty plasma. And so throughout this presentation, my plan is to give you kind of a brief introduction to what plasmas are, to talk a bit about dusty plasmas, and hopefully motivate some of the interesting things that we do here. And so, like most of the things you do in physics, you can't do them alone. I have a fairly large research team. I have a collaborator, Una Konopka at Auburn University. Bob Merlino and Marlene Rosenberg are my collaborators at Iowa and UCSD. I've got technician. These are all grad students, a small army of undergrads that work for me. And I have to acknowledge that all this work is supported by DOE, Department of Energy, NSF, and the NASA Jet Propulsion Laboratory. And so what I plan to talk about today is sort of the basic properties and applications of plasmas. And one of the more interesting applications of plasmas is nuclear fusion. So I'll talk a few minutes about that. Then I'll talk a bit about our dusty or complex plasmas, and then move on to two big topics. One is our magnetized dusty plasma experiment, where we're trying to actually trap these little particles with magnetic fields, and I'll also talk a little bit about some of the microgravity work that we're doing, which I think is actually pretty cool. Okay, so moving forward. So one of the big things, especially when I talk to audiences of undergrads, is what exactly do we mean by plasmas? And so I would argue that if you take physics, and most of the physics that we talk about, especially in an undergraduate class, is Newtonian physics. It's the physics of objects, about people-sized objects, maybe as big as a planet. But Newton came up with a formalism to describe all of that. But now, if you extend physics beyond Newtonian physics, and you start making objects move really, really fast, then that takes you to the part of physics known as special relativity, and that's the work by Einstein, where you've got objects moving very fast. These are high fractions of the speed of light. Another branch of modern physics is when objects get very big, and this is now much bigger than planets, but say objects the size of black holes that have hundreds of thousands of solar masses, or the sizes of galaxies. When you've got that much mass in the system, there's another branch of physics, also defined by Einstein, called general relativity. And then, of course, there's the physics of the very small. And hang on a second. Oh, are we still good? Because I just lost the audio. Wait, hang on. Can you guys still hear me? Just nod if you still can. Oops. Oh, can you guys hear me? Oh, okay, okay. I just can't hear you. Okay, sorry
Yeah,
about that. Okay.
we're good.
Oh, it just got really quiet on my end, and so I just thought I lost everyone. Okay, so I'll keep going here. Big, fast, really tiny. Is quantum mechanics, and so that's objects that are really small. And of course, there's the connections between things, like stuff that move really fast and really big, which is astrophysics and cosmology, or objects that are really fast but really small, which is like particle physics. And there's also the options of trying to connect things that are very big and very small, which is trying to come up with theories of so-called quantum gravity, which is string theories. Now, the problem is that plasmas don't lie anywhere in any of this set of stuff. And so I would argue there's another branch of physics which is called the very complex. And these are where you have systems that are governed by the equations of Newtonian physics, but you have so many particles in the system that to try and model the interactions, you have to use statistical mechanics and other types of techniques. And systems like weather and fluids and plasmas all fall under to this category of physics we could call very complex. So that's kind of where plasmas lie. They're in this regime where you can treat most of the equations with very classical physics, but there are just many interactions. In the case of plasmas, we're talking, well over 10 to the 10 to 10 to the 20th nonlinear coupled interactions between the particles. So a plasma, as most of you probably know, is where you take a system, is a state of matter, where you take a system from going from a solid to a liquid to a gas, each one of these adding more energy to the particles, and then eventually moving to a plasma where you've actually gotten the molecules moving so fast that they make ionizing collisions, and so that the ions and the electrons can stay separate from each other. And so this chart that I just popped up just kind of gives you kind of the parameter space where you might find plasmas. You can have very low density plasmas to very high density plasmas, and they range in temperatures anywhere from hundreds of Kelvin all the way up to millions of Kelvin, the type of temperatures you find inside the center of stars. So plasmas are what you could almost argue are kind of a hidden technology, because man-made plasmas can occur, man-made and natural plasmas occur at a whole variety of scales. If you start here at the smallest scale, looking at manufacturing, we use plasmas to help us etch the circuits that go inside of computers. And it's been through a technique called plasma processing, where you can make features well down to the tens of nanometer. Those are the feature size that you get in computer chips, and plasmas are an integral part of that manufacturing. Of course, you've got things like fluorescent lights. The middle picture here where the arrow is now, this is a relatively new and emerging area of plasma physics called plasma medicine. That's not a Photoshop. That really is a discharged plasma actually striking a person's hand, and they actually use that for things like wound healing or sterilization, and this is called an atmospheric pressure plasma. So that really is a plasma outside of a vacuum chamber. Of course, you've got laboratory experiments and fusion energy, and I'll talk a bit about fusion energy in a moment. And then for naturally occurring plasmas, you've got stuff like lightning, space weather, which is the connection between the sun and the Earth's magnetosphere, where the sun ejects the so-called solar wind that interacts with the Earth's atmosphere, Earth's magnetosphere, and then creates a bubble of plasma that surrounds the planet that gets trapped on the magnetic field lines of the Earth. You've got phenomena like astrophysical jets, these are structures that are many light years across. Again, they're powered by black holes through a plasma phenomenon known as a magnetorotational instability. And so that's what's proposed as a mechanism to give rise to the converts the angular momentum of material falling into a black hole into these energetic beams that you can see coming out of the tops and bottoms of galaxies. And of course, plasmas are really important for stars and planet-forming regions of space. The probably the thing that, if you've heard about a plasma before or encountered plasmas, has been in the idea of fusion energy. And nuclear fusion is the process in which you take two light atoms. In this case, you're taking two isotopes of hydrogen, deuterium here and tritium here, combining them under conditions of very high temperatures and high densities. They fuse and then release a helium nucleus, an alpha particle, a 14.1 MeV neutron, and then you can extract out a lot of thermal energy from this process. And this nuclear fusion process is the process in which how stars work. And for almost 50 years, we've been trying to actually make that same process occur on Earth. This is an example of the largest fusion device on Earth, which is the JET tokamak in Europe. On the left side, you can see the vacuum chamber. It's shaped like a giant donut. It's got a big center stack in the middle, and it's kind of hollow. This side shows what it looks like without the plasma, and then this side here is what it looks like with the plasma. One thing I want you to notice is that most of the plasma, this hydrogen plasma, is actually transparent, because for hydrogen, you get your emission lines from electrons changing energy levels, and if you've got your plasma, your hydrogen plasma fully formed, you should have pulled all the electrons off, and you shouldn't be seeing any emission. But you do see these bright white spots here along the walls. This is where impurities are coming off of the walls and leading to the emission of a lot of light. So this would be carbon or metals that are giving rise to where all the light is. But what you really want is the center of your plasma to be virtually transparent, because that tells you that you've actually ionized all your gas. As big as JET is, and it's about 4 meters across, it's a baby compared to what we're building now in France. And if you look really carefully, right there is a guy, or a model of a person standing right there. This machine is actually under construction right now. It's called ITER. It's being built in southern France. And if ITER is successful, well, here's that pink plasma again. It's like the plasma over here. If ITER is successful, it will be the first fusion device that will actually produce more power than we use to actually create the plasma. And so this is a consortium of something like the 7 partners, the United States, Russia, China, Japan, the European Union, South Korea, and I am forgetting one. I got to 6, so I'm trying to remember the 7th one right now. It'll come to me. And it's a huge project. I said that JET here was about 4 meters across. ITER is about 20 meters across. So it's a huge device. It's being assembled by a big international consortium to put this together. The first plasma in ITER is targeted for sometime around 2021 or 2022. So it's a very complicated device to build. At this point, the site has been prepared, and I think that the lower half of the support structure to hold the actual experiment on has just been built. Okay. So going from sort of the big global issues to what we do here at Auburn. At Auburn University, we have a department that consists of about 23, 24 faculty members, and we're engaged in condensed matter physics and atomic physics, and our biggest area of work, however, is in plasma physics. And as you can see here, almost half our faculty are actually engaged in some sort of plasma physics research. And because we've got a sort of a big effort in plasma physics, our department actually is broken up into several different groups that all work on plasma physics. We have a group that's working on some microgravity experiments. We also have a fusion experiment here. This is called the compact toroidal hybrid. We have a number of faculty members working in the area of space plasmas, looking at the both satellite data as well as theoretical models of how the solar plasma interacts with the Earth. So this is a picture of the Earth's magnetosphere. And then these three pictures over here on the right side of the screen, these are experiments that I have in my laboratory, the Alexis experiment, VPX, and this machine here called MDPX. And I'm going to talk a bit about two types of projects that we do in our lab, this microgravity lab, and I'm going to talk about the magnetized dusty plasma experiment, MDPX. You know, if you're interested, you can always ask me questions about some of the things that we do in some of these other devices. You know, some of the fusion work or the space plasma work, which is in and of itself really fascinating. So let me go start the movie, and hopefully you can actually see the movie and see this thing actually oscillating up and down. That's a dusty plasma. That's not a simulation. That is actually that's experimental measurement that was done by one of my undergraduates several years ago. And what I hope you can see in here is a couple of different features. You can first of all see the slow rotation of the particles over here. You can see this wave activity going on over here. There's that weird line that's there in the middle right there. These are all features of things that we're really interested in that make dusty plasmas pretty unique. So what exactly is a dusty plasma? It's a 4-component plasma. So a regular plasma has 3 components: the ions, the electrons, and the neutral atoms. And a dusty plasma has this additional component, which is this charged dust grains, these little tiny particles that are floating around in the plasma. My father refers to these as after all these years in school, he said, you actually are just putting dirt into a plasma and, you know, trying to study it. And I said, yeah, that's exactly what I do. Those particles collect ions and electrons from the background plasma and become charged. And as I'll talk about in a few minutes, they actually, as a result of them getting charged, there's a force balance that allows them to float in the plasma. And what we do is we try and study how the background plasma changes because the dust is in there. We want to study these types of instabilities and the waves. And one of the things that I'm going to focus on, I'm going to talk about how we make measurements of the dust particles, because we want to understand what the forces are, we want to understand the electrical properties, and we also want to understand something about the thermodynamics of this system. So again, why should I care about floating dirt? Well, I mentioned plasma processing, and so this is like the great example from early in our field. So there's a cute story that for many years, when people tried to do plasma processing, they thought that from the employees, and so they kept making these really advanced clean rooms. And then finally, someone took a laser, which is back there, and shined it inside the plasma processing chamber, and they saw all of this stuff that was actually floating around in the middle of the experiment. And what was happening was that the plasma was actually forming dust. It was actually taking particles, taking the material that was being etched off of the surface, coagulating it, and actually forming little particles. And while the particles are floating in the plasma, it's not a problem. It's what happens when those particles fall back down on this really nice expensive computer chip that you're trying to make. And so it's a huge source of contamination. Similarly, you also have those contamination issues in fusion. This is a picture from the bottom of a fusion device showing all of this material that's actually just got knocked off of the walls and forming little spheres and chunks and just, dust, dirt, which is a source of contamination. So we want to understand how to control this. But in naturally forming environments like planetary nebula or planetary ring systems like Saturn, the physics of charged dust is actually critical to understanding the dynamics of things like Saturn's rings and planetary nebula. Okay, so this is a physics talk, so we have to do a little bit of physics. All right. So what we want to do is we want to understand how the dust particles become trapped, and we want to understand what the physical limits are on a whole variety of experiments that we can do with dusty plasmas. And as I said before, our scientific goal is we want to measure, and the thing I'm interested in at least, is transport. I want to understand how particles and energy and waves move around in the plasma. So that means I need a technique that's going to allow me to make measurements of how the particles are moving. And so here's the physics bit. If I can measure the position of the particles, and I can track how the particles move from one time period to another, then I can get the velocity. Now, if I can get the velocity and I can figure out how the velocity changes, then that gives me the acceleration. Now, once I have the position, the velocity, and the acceleration, now that's really important because now it's now possible to get to the net force. Because if I have the acceleration, that tells me that there's a sum of forces, and it tells me what the sum of the vector sum of those forces are. So now I can get the forces. If I have the velocities of the particle, and I know how the velocity changes, well, that's like a change in kinetic energy. And again, if I know the kinetic energy and something about the forces, now I can actually go and make measurements of the total energy of the system. And if I can measure the total energy, then that means I can get information about the thermodynamics of the system. So that's the physics. If you know the position and the velocity and the acceleration, then you can get the forces and the energy, and then I can ask myself all sorts of really interesting questions about the physics of the dusty plasma. So if there's nothing else you get out of this talk, that's kind of this is the physics punchline right here. So how do we measure the velocity? Well, what my group has done, we've developed a couple of different techniques to do that. One of the techniques is called particle tracking velocimetry, or PTV, and another technique that we use is called particle image velocimetry, or PIV. And so there's kind of a regime for each one. PTV works best if particles are moving slow and there aren't that many of them. So it means that you can see each individual particle. PIV works best in high-density, high-speed systems, so that if you've got lots of particles all moving together and in a kind of a fluid-like behavior, then PIV works in that regime. And so what we work on are developing techniques that apply both PIV and PTV to make measurements of the particles. And over the years, we've developed what we call if you use a single camera with a laser, we can use PTV and so-called 2D PIV. And what it does is it measures the velocity of the particles in the plane of a laser sheet. And if I use two cameras, kind of like your eyes, they can give you stereo vision. We can use stereoscopic PIV or stereo PIV to measure the 3D motion, the Vx, Vy, and Vz of the particles. And the idea is that if I can measure measure the particle positions and get to their velocities, then I can begin to do really interesting physics on them. So this is so I'm not going to talk so much about the details of each of these technologies, but whenever you see images that I have that show a bunch of arrows of particles moving, I'm either using PTV or PIV to reconstruct the motion of the particles. Okay, so talking about the dust itself and some of the interesting things you can do with the physics of the dust, well, one of the really cool things is that the dust particles are charged. And they get their charge from picking up ions and electrons in the background plasma. Or if you've got a radiation environment, then you can get photoemission. Like say, for example, UV radiation can kick off electrons. Or if the dust grains are really hot, then you can get things like secondary electron emission or thermionic emission, basically electrons being given off because the dust grains are hot. And basically the punchline of this is that the dust grain charge is a result of an equilibrium of a bunch of different properties, electrons, ions, secondary emission, all sorts of other things. And what you get is that the dust grain charge can actually fluctuate. It's not a constant. And that's something that actually makes part of the physics of a dusty plasma really interesting. In the laboratory, the dust grain charge is almost always negative. But in space, dust grain charge can either be positive or negative. And so one of the things that we want to study because of that is how charge gets removed in the plasma. So I'm going to show you some data on that. This is from a paper that my group did a long time ago, back in 2000. There's a plasma up here, and there's a dust cloud down here. And this is a really old experiment, so none of our videos are really great. But we had a probe that we could put into the plasma, and the solid curve, the solid dots, are when there was no dust in the plasma. And the open circles are when there was dust in the plasma. And the thing to basically get out of this is that what happens is that when the dust was added to the plasma, there was a reduction in the number of electrons in the plasma. So a bigger number means more free electrons. And so that means that the dust particles had captured some of the free electrons in the plasma, and we're now holding those particles. So that's how we know that the dust was negatively charged. And this is just one example from many experiments done in the early 2000s to confirm the charge of the dust grain. This slide's got a lot of numbers on it, so don't worry so much about that. The punchline is that the dust particles are heavy and slow, and that means that gravity is really important for our experiments. And to put it in comparison, the electron mass, if that's 1, then the ion mass would be like 10,000, but the dust mass would be effectively 10 to the 16. 10 to the 16 times bigger than the electron mass, or like 10 to the 12 times bigger than the ion mass. So that means that the dust particles compared to the ions and the electrons are heavy, and they're slow, and therefore the gravitational force on them is really important. This has some other effects having to do with the fundamental frequencies of the plasma. That's what's listed here, and I can come back to that if anyone's interested in that. But basically what it means is that you can study all sorts of low-frequency waves and flows in plasmas because gravity is important. And now, again, I'm not sure how well this is going to show up, and you'll have to give me some feedback on this. I'm going to start... Okay, so can you see that one? Yeah. Okay. So then how about this one?
Yeah, I think we can see something.
Yeah.
So, okay, over here there should be something spinning. Do you see that?
Yes.
Yeah.
Okay. And then a little fountain thing over here. Okay, and then there's this other one here, I think. You should see two things spinning.
Yeah. Oh, cool.
Okay, so that, let me see if I can start these one at a time. I'm going to stop this one, I think. So the one over here, I'm going to stop this one too and then come back to it. So this one over here, I have no explanation for. It's one of the coolest things we ever measured, but we're not entirely sure what we were looking at. It's some sort of weird dust fountain that was occurring in the experiment, but it's pretty pretty. That's what's cool about it. I'll go to the middle one again, and this middle one is actually a torus of dust, and that means it's kind of a donut. So if you kind of carefully watch the video, and as it cycles through, the laser is going to start at one side, the back, then it forms these rings. Now you can imagine if you come up to those rings and you come to the front, it goes away, and then now you're scanning the laser to the back again. So it's forming a little donut, a little torus in the middle of the experiment. And then finally, this one here shows a close-up of some wave activity that we get in the experiment. And this was like the video that I showed at the very beginning, but now you can really kind of see the detailed motion of the little particles in the waves. So this is just some examples of transport and some of the really fascinating things that we actually see in the experiment. The other bit, and I'm going to let this movie play out here because hopefully this is going to work. I'll just talk over it while it's playing. A really cool feature of the dusty plasma is that the particles can self-organize and create kind of new states inside the plasma. And so if you're seeing this play here, you shouldn't be seeing very much, except that the particles are kind of shaped like in this hexagonal pattern. If you look at any dust grain, it's got 6 particles around it. So like, okay. As it moves into the second phase, we're going to start heating it. And what's going to happen is that this crystal structure that you see here is going to start getting more and more mobile as you're adding more energy into the system. And hopefully you can see some of those odd features there. Now you're going to go, in the next step, you're going to go into the so-called vibrational phase where you're now actually going to start melting the crystal.
Oh, wow.
And now you're losing the short range, a lot of the long range order is breaking down as the particles are kind of becoming heated even more and becoming, and the system's melting. And then finally, in the last transition, the system is going to go through its disordered phase, which is basically going to turn it into a gas. Okay.
So, Ed, is that a two-dimensional system, or is that just a 3D system that you've imaged a 2D plane with your system?
No, in this particular case, this is some data from my colleagues in Germany. This really was a two-dimensional system. So each particle, each of the dust grains in this experiment is exactly the same size. So these are very expensive little particles. These are like something like 3.2 plus or minus 0.01 micron diameter particles. Very, very uniform. And they all basically sit at the same vertical layer in the plasma. And so this gives a wonderful example of the ability to be able to take a dusty plasma and form a solid-like, a liquid-like, or a gas-like system of particles that are already inside of a plasma. And you can now do things like study the fundamental physics of phase transitions and melting and all sorts of soft condensed matter type systems using a plasma. But what's really cool about it is that you can actually watch the melting occur at the particle level. Not just like the whole system melts. You can actually watch as individual particles become heated up, which is really cool. So that means that we can study some of the thermodynamics of the dusty plasma. And this is a complex slide, so I'm not going to spend a huge amount of time on it. But basically, this is something that my group spent many years on. I have 2 PhD students in recent years that have actually spent a lot of their PhD dissertations actually understanding as we change the pressure in the system, for example, and watch the system melt. We were able to look at waves propagating through the system and use that to make measurements of the temperature, and we were able to measure properties of something called distribution functions. This is some of the work that my student Ross had done, and all of these are accessible because we can do these velocity measurements of these systems.
Mm-hmm.
Okay, so for the last little bit here, what I'm going to focus on is two aspects of things that we do now. One is microgravity studies, and then the other one's going to be dust and magnetic fields. And so the question is, why would you want to do these studies under microgravity? Well, I said on one of the earlier slides that the dust particles are slow and heavy compared to the ions and the electrons. And so very early on in our field, people had this idea, well, if gravity is what's kind of dominating the experiment, then we should get rid of gravity. Simple as that. Now, the problem is when you do an experiment on the ground, the particles have to be lifted up against gravity. And there's a zero-order force balance which says that F gravitational, basically the downward force on the dust grains, has to be equal, has to be compensated, most likely by an electrostatic force. However, if you move the system into microgravity, basically make gravity go away, then what happens is the dusty plasma goes from being really compressed towards the bottom of your experiment, and it expands and fills up the whole plasma volume. And you can make very large systems. So over the last almost 20 years now, driven in large part by our colleagues in Europe, there have been a series of experiments on the space station, on the International Space Station, well, first actually starting on the Mir space station, then later on the ISS, to study the physics of dusty plasmas under microgravity. They first started here with some parabolic flights. We also do experiments on the Vomit Comet, on microgravity airplanes, which is really cool. I've had the opportunity to do that myself. That was great. And starting in 2001, 2002, there have been a series of multiple microgravity experiments. First of all, PKE, then PK3+, PK4, which I will actually talk a little bit about, actually launched in November of 2014 and has been on the space station now for about the last year. So this PK4 experiment is the newest one, and I actually here at Auburn, my colleague Uwe and I are both on the science team for PK4, so we actually have access to some of that data, and I'll actually show you what some of the microgravity data looks like. So if you do an experiment without if you do an experiment in the lab, the biggest problem is that here's this gravitational force acting down on the dust grain, and you always have to basically lift the particle up against gravity. Now, in reality, there's all these other forces, it's so-called drag forces and radial confinement forces and interparticle forces that are at play in a dusty plasma. But because of this force, this gravitational force, you're always fighting gravity. And so the advantage of moving to microgravity is that you can study some of these smaller forces. And so this is gives you an example of an experiment on PK4. This is the ground-based version of PK4, and it's a plasma inside this U-shaped tube that's right here, and we inject particles, and then we study the particle flows. And then here's one of these PIV maps that allows us to look at the velocity as the particles are flowing. And if I replay the movie here, what you see is that the particles under lab conditions are getting compressed. They start off kind of filling the whole chamber, but the whole thing kind of gets compressed in the presence of gravity. And that's one of the things that we're trying to beat. So these are some early images from an experiment on PK4, the same instrument that was on the previous slide, but this is now what it looks like on the space station. It was launched to the space station in 2014. Installation was in November of 14, and these are images from the first data runs back in May of last year. And what's really cool about it is that instead of the cloud compressing actually over time you actually see the cloud expanding, because as the particles get charged up, they start pushing against each other and actually pushing against the dust cloud. And it's you get some really fascinating features in here. This stripe in the middle is when they turned on a laser and they were using a laser to push on particles through the center of it. In the future, what we're doing here at Auburn, my colleague Uwe is designing some hardware for what we think is going to be the next generation experiment after PK4. And this is a device called Plasma Lab. And there's a couple of different options for it. One is cylindrical, the other one is spherical. And we actually have a version of the spherical chamber here. And then this is some parabolic flight data showing some of the really just beautiful phenomena that you get in a dusty plasma under microgravity. And there's just all this richness, this waves. Up here, there's this giant hole in the middle, which is called a void. Yeah, don't ask me too much about that. Well, actually, I know a lot about it. It's just very controversial at the moment. It's one of those things that we don't like to talk about. But you get this wonderfully rich type of system, and you only get the clouds to look like this under microgravity. Okay. And now for the final, so that just gives you a really brief introduction to some of the stuff we do with microgravity. Let me talk a little bit about the experiment that I'm the principal investigator of, which is on magnetic fields. And so, as we've talked about, a plasma is made up of charged particles. And if you've taken your introductory physics courses, you know that a charged particle will have a cyclotron motion around a magnetic field line. And that's kind of illustrated here in this little movie here. Here's an example of a charged particle going around a magnetic field line. And for a whole variety of plasma systems, like coronal loops on the sun, or in laboratory plasmas, and this is from our Alexis experiment, we can actually confine the plasma with magnetic fields. And so a question in dusty plasma research has been, almost all of the experiments have been done in the absence of magnetic fields. And now we want to actually understand, can you actually do an experiment with a magnetic field on the dust? And actually see whether or not could you make a dust particle do this type of cyclotron move, in a magnetic field, which would be really cool. Now, there are a variety of reasons why you want to do magnetized dusty plasma. There's a number of direct effects that couple the plasma to the magnetic field, and they may change the properties of the dust. For example, ion flows and charging and things like that. There's also a number of indirect effects having to do with how the particles grow, whether you can form 2 and 3D structures, the coupling between the particles, that may be indirectly affected by the magnetic field. So this is kind of what we want to explore in our experiment. But the problem is, it is extremely hard to magnetize charged dust. And here's why. If the red represents the size of an electron orbit, then the green represents the size of an ion orbit. Not to scale. The charged dust its orbit is huge. And if I were to draw it to scale, if the electron orbit were, say, a micron across, then this dust orbit would probably be in the order of a half-meter diameter. So it's really hard to magnetize the dust. And there are a whole variety of equations that we can use to try and parameterize that. we can use something called the gyro radius, which is the radius of that orbit compared to the size of your experiment. Or there's a collision frequency argument that you can make. Or you can look at the magnetic force to the gravitational force. But in all of these equations, there's a common feature. There's a ratio of B over A. B is the magnetic field strength, A is the size of the particle. And all these equations tell you that you have to maximize B over A, meaning that you want to use a really big magnetic field or you want to use really small particles. But we're constrained because you want your particle to be big enough to take advantage of all the dusty plasma features so that you can see them. So if that sets your A, then that means that you only have one free parameter, which is B. And so I'll give you the punchline. B has to be several Teslas.
Wow.
So we designed an experiment along with our collaborators to build a magnetized dusty plasma experiment. And especially for students, I just want to give you a sense of how long we've been working on this. In 2003, it was an APS meeting, American Physical Society meeting, where the group of us that eventually became the PIs of this project, we were sitting around and just beginning to talk about this with somebody from the National Science Foundation. Flash forward through a lot of pain, suffering, rejection, meetings, lots of stuff. We finally got a grant in 2011, almost 3 years later, after that first meeting. And it still took another 2 years to actually build this experiment. So at this point, it's 7.5 years since we first came up with this idea. So it's been a long process. And this is what the device looks like. It is 159 inches. To put that in perspective, that's 13 feet. It's it's over 4 feet across, and it has a 50-centimeter bore. Now, these drawings are technical drawings. They don't really mean much to you, so I'll bring this image up. That's me standing next to the experiment, right after he got it installed in the lab. I'm 5'8", so it's pretty big. The magnetic field is 4 Tesla is the maximum, and we've actually operated it up to 3 Tesla so far. One of its really neat features is that we can program a magnetic field gradient, which is really cool. It's a superconductor. So it uses ionic titanium superconductor. Something like 100 kilometers of superconductor is actually inside of this. It actually has 4 coils, a small one, a big one, and a small one. And they can each be individually programmed. The whole thing you're looking at here is about 3 tons. But the cold mass that's inside of this cryostat is 2.5 tons of superconductor. And so it takes, because we don't use it, one other feature is that it tilts. So the whole, you can see a motor right here. The magnet can tilt from being vertical to horizontal. So that means we couldn't use any liquid helium, so it has to be cooled using a technique called using cryocores. And it gets down to a temperature of about 4.5 Kelvin or so from room temperature. It takes 17 days to do that. So it takes a while. So this was my baby. This is the vacuum chamber on the inside, and you can see the glow of the plasma. And then this is when we're lighting up the inside to look for dust particles. And this is an overview of the whole lab right here. We make a type of RF-generated plasma, and we've used particles from 0.5 micron up to 8 micron diameter. We use high-speed imaging, a whole variety of technical tools for this experiment. One of the really neat observations that we made in this experiment is that I showed you before that the dust forms these hexagonal patterns. And actually, let me jump to the next slide, which shows it a little bit better. There we go. So this is the image that I showed you before. And without a magnetic field, the dust forms these hexagonal patterns as it goes into this solidified state. And in order to do that, you have to actually raise the neutral pressure, the amount of gas you have in the system, quite high. And the reason you do that is to lower the temperature of the dust particles. Because in order to get to that state, you have to basically take away their kinetic energy by colliding with gas. In the magnetic field, one of the really neat and most immediate observations that we made was that the dust didn't form these these hexagonal patterns. They form square patterns. And they form the square patterns at low pressure, not at high pressure. So it behaved exactly the opposite of what happened without the magnetic field. And we think that it has to do with some sort of boundary effect in our experiment. And that was what I'm trying to indicate here on the other slide. We've actually tried an experiment where we had two grids, and the particles actually conformed themselves across this boundary and locked themselves in a pattern of two different grids. We still don't understand all the physics of it, but I will say that we can publish it because there's the paper. And we actually just published a second paper on it too. So it's pretty cool. Again, for the students in the audience, you don't always have to understand something to get it published, right? I'll show you one other really cool feature of what we see in our dusty plasma at high magnetic field. Also, I'm sorry, I should have said these measurements were done here at 1.5 Tesla. I'll show you another measurement that was done at 1 Tesla, and we'll start the movie. These are the same types of waves that we saw before, but now you've got these really odd features of this weird V-shaped structures in there. We're not sure exactly what those are. And if you look at the particles at the bottom, not only are they moving up and down, you'll see that they're actually drifting from left to right a little bit as well. And that was odd to us until we realized that, oh wait, we're sitting in a magnetic field. And not only is there a magnetic field, there's also an electric field present. And again, this is something you may or may not have come across yet in class, but there is a type of motion that you can get that is in the direction of E cross B. So there's a B field coming down, a magnetic field pointing down, and it turns out that in our experiment, there's an electric field that's pointing in the X direction. So that should mean that the whole cloud actually has a rotation to it. And so recently what we did is to follow up on that original experiment, we did a second experiment. And here what you're seeing in the top movie is a side view, like the one that I showed you before. But here is a simultaneous movie that we made from the top. And now you can see those particles actually circulating around. So what it is you're looking at the same laser slice that in the side you can see the whole cloud, and at the top of the cloud you can actually see the particles circulating. And then what we did is we did PIV measurements again and showed that there's the circulation behavior. And in fact, not only is it circulation, it's also got share in the circulation. Those are details, but suffice it to say, this was something that was not quite predicted, and we're pretty happy that we were actually able to observe this and actually confirm that not only are we getting the waves moving up and down, we have got some strong particle transport moving in this circulation direction. Okay, So that's some features that we see in this experiment. So I'll end up by saying the following: in our microgravity studies, our goal on the ground was to make studies using to show that we can do these PIV studies. We've just gotten our first data from the space station, and there's already a pretty rich environment for particles and waves and things like that we're seeing from the space station. And then in the magnetized density plasma, I showed you two different phenomena. I showed you this self-ordering of the system and showed you some of the waves. And we have an incredibly long to-do list looking at the grain charge and magnetization, a feature, something known as G cross B, where we're trying to understand the motion of the particles when we orient the experiment horizontally, looking at 3D structures, and there's just sort of a whole rich variety of things that we can do. And with that, I will pause here, and I'm going to switch back my video, hopefully, maybe, to me, and I'll be happy to answer any questions that you might have.
All right, let's give our seminar speaker a round of applause.
Okay, can you actually see?
Ed, you just kind of went into another view there. Could you?
Okay. Hang on a second. I am trying to.
There you are.
Oh, there you go. Right. There you go. I'm back.
Wow, that was phenomenal. Really interesting.
Okay.
Do we have any questions from our audience, either here locally? Lucas, ask a question.
So I was a little bit confused about the different phases that you showed from the stuff out in Germany, how it was a solid and then it turned into a liquid and then it turned into a gaseous. That was the dust inside the plasma. So you're saying that the dust is not the phase changes inside the stuff.
I'm sorry. I got a little bit of feedback there. So I heard the first half, which was you were a little confused about the solid to liquid to gas transition.
Inside of the plasma.
Right.
So it's behaving differently than a normal. Would it behave differently than a normal PVT curve or pressure and stuff? And so that was just basically you were measuring how it would behave in the different phase changes.
Right. So I'm trying to think of the best way to describe this. So what we think we are seeing is we load the system with particles, and we prepare by adjusting the plasma conditions to force the dust particles to have a particular orientation. So if I raise the pressure, the particles line up in this hexagonal grid pattern. Okay? We have a way of characterizing that using a property called the Coulomb coupling parameter. And once the Coulomb parameter gets above a certain value, then we can say that the system is strongly coupled and is now solid. And then we can change the system, and as we change the system by essentially melting the crystals, we measure that coupling parameter, and then that coupling parameter can go into a liquid regime and then a gas regime. Okay. And now I had some echoing there. I hope it wasn't as bad for you.
It did start to echo a little bit, but I think I got the general.
Okay.
Right. Right. All right. Do we have any questions over at Suffolk?
I have a question. There, when we saw the hexagonal pattern, was that dependent on which particle was put into the system, and so would other particles create different lattices there, or
no?
Was
That's a good question. No. I picked a random particle and drew that hexagonal pattern. When the system is in a strongly coupled state, I should be able to pick any particle, and it should form that hexagonal pattern. And that's the self-similar property of the system. So it doesn't matter where in the system I look, or actually, let's see. Let me do the following. I can pop this. So if you give me a second here, I can do a thing. Okay. Okay, so I pick this particle here, and you can see there's 6 particles around it.
Mm-hmm.
I can pick that one, and there's 6 around it. Pick that one, there's 6 around it. So even if I pick that one, the one next to it, it also has 6. So that's the self-similar property. Okay.
So they're not all the same type of dust particle. They're different, just random particles inside.
No, they are all exactly the same particle. Okay, so we had to load the system with, in this case, a few thousand particles that were exactly the same.
There, depending upon who teaches the class and what you cover, that two-dimensional gaseous state is one of those problems that usually you see in your stat mech or your intro thermodynamics, your sophomore, junior level stat mech kind of class. And that's just so beautiful that you could see that actually in the lab, and it go from a esoteric problem in a book to now being something you can actually study. That is just beautiful.
Yeah. What also is really neat about it is that because the system is two-dimensional, it turns out that two-dimensional melting and three-dimensional melting do not occur the same way.
Cool.
And so you can actually study the differences between 2 and 3D melting with these types of systems.
Wow. That's really cool. So does your lab have any summer research or REU programs that are running? Because it sounds really fascinating.
We are actually in the process of applying as a department to reinstate our REU program.
Cool.
Within my own lab, our plan is we're transitioning to a user facility type operation. And we're not quite there yet, but the plan would be within a couple of years to have some sort of summer activity. Right now, the students that we bring in tend to be graduate students who are working on their PhD projects, and we've had a student from South Korea and a student from Germany already come to do experiments on our facility.
Cool. Cool. Question.
So a lot of the findings that you talked about, the way that you talked about it made it sound like you were just messing around and said, oh, look, it does this cool thing, and it does this cool thing. Has that been kind of what you're doing, or are you really trying to find specific things?
That's a really good question. We have some very specific things that we are looking for. One, in order to study the true magnetic property of the dot, which is our main focus, there's a target magnetic field. We need to do that. That is 3.3 Tesla. As I said, we've gotten up to 3. So we're still just below the threshold where a lot of the interesting physics that we predicted should emerge. However, no one has ever performed a dusty plasma experiment in which the ions and the electrons are fully magnetized and the dust is at the threshold of being magnetized.
Hmm.
So this regime that we're operating in right now between sort of 1 Tesla and 3 Tesla is essentially unexplored territory.
Wow.
So in that respect, the first part of what you said, we had no idea what we would find in that regime. And so in the proposal that we wrote, we actually said, well, the way the experiment's going to go is we're going to first magnetize the electrons, then the ions, then the dust. Now, we're not quite at dust magnetization yet, but we can definitely magnetize the ions and the electrons. And there's a whole slew of new physics that's emerging that, like the whole four-corner dust thing, there's no theory. Because theorists didn't predict that that would happen. So we haven't gotten to full magnetization yet, and this is the absolute truth. We published 3 papers last year, and we aren't even at full field.
Wow.
So we're just, every day you go into the lab and you go, well, let's go do some new physics today. And, turn it on. And you go, oh, no, what's that? Somebody write a paper.
Somebody write a paper.
So it's been a little bit of both. I'll tell you, one of the main things that I personally want to look for, I want to see the dust gyrating, going around the magnetic field. That to me is the holy grail experiment. If we can see that, wow, no one will have ever seen that before. But we do need a certain minimum magnetic field to do that, and we're almost there. So, but that's a big question.
All right. Anything else? Do we have other questions? Let's see if our Suffolk people have a question before Lucas jumps in again.
I guess we're
pretty thorough presentation.
Okay. Yeah. Oh, thank you.
All right, Lucas, go for it.
So in your presentation, you mentioned how long it took to get the experiment going and really get everything designed and stuff like that. 7 years is a long time. And so you also called this machine your baby. What advice would you give to scientists that are coming up into the field who have an idea of what they really want to do and are getting shot down at where they want to go?
So there's a huge caveat. I have been working in dusty plasma since 1998. So when we started talking about this magnetized experiment, I was already working in the field for 10 years. In 2007, as the year, I made full professor. But that's really important in this story, because I started talking about this crazy idea in 2008. So, as a junior faculty member, most of my experiments were basically this big. They were 20 inches across by about 10 inches tall. They're all really compact. There's a lot of very interesting physics you can do in dusty plasmas with very small pieces of hardware. To be honest, it took a certain amount of seniority in the field to propose an experiment like this. Again, to put a scale on it, I could build one of these small experiments for $20,000. If I go really cheap, I have built a dusty plasma experiment for as little as $500.
Wow.
This project was $2.5 million.
Wow.
So it's something like almost 200 small experiments. So you couldn't propose this as a new faculty member. So we had to carve out a niche. We had to do a lot of hard work to. Most of my original work was in this thermodynamics of dust, this development of PID and all of that imaging technology. And it took a long time to convince people that we were going to be the right team to build a project of this scale. So I would say for someone getting into any field, you're going to get trained as an undergraduate. You go to graduate school. You learn your skills in graduate school, and through the course of learning about the physics field and the physics profession, you'll have opportunities to define a particular project, a particular niche. And at some point, you're going to go, I really want to do something ambitious. And, but it takes a while to kind of, decide, okay, this is really what I want to do. So, I had 4 other experiments built before the magnetized one. I don't think anyone should have given us the money to build this if we hadn't had the experience of building all of that other hardware before.
Right.
So it's a long process, but it also was very carefully thought out. Yeah.
What do your grad students go on to do after they leave your lab?
So I've had 7 PhD students so far, and I have 5 currently working for me. The 7 so far, let's see, 1 is now a tenured professor. Let's see, 2 are working in industry. 2 are working for national labs, and 2 are postdocs. So they graduated just relatively recently. So my PhD students have gone on and done a whole range of stuff, from industry to national lab. Let's see, Eric is about to become a section head at the Naval Research Lab. One of my guys works for Google. One of the industry guys works for Google. But the other one works for Intel, and he now makes the computer chips that goes into all of your computers. He runs one of their fabs, and he runs something like it's a $3 billion fabrication system that they turned over to him, which is insane to me. But his job is incredibly stressful because it's he has 2 cell phones on him at all times, and he's been told that if the fab goes down for more than 2 hours, the company is starting to hemorrhage money at the rate of like $1 million an hour. So no stress.
That's stress.
Yeah. Big undergraduate is stressful.
So plasma science and research there is a good preparation and intro to any sort of industry, either academia or national lab sort of work, or even regular industry, industrial physicist kind of jobs.
Yeah. I mean, I think our students here, not only in the plasma group but throughout the department, have taken sort of the full variety of jobs. I've had since this is an audience of mostly undergrads, I've had about 30 undergrads work for me in my lab over the years, and they've gone on to become professors, medical doctors, pick a profession, almost pick any science-based profession, and I've got an undergrad in it.
Cool.
So,
what advice might you give to current undergraduates, either looking to go to grad school there at Auburn, or pursuing other sorts of fields that you feel like sort of skill set they would really benefit from having to be able to get plugged in and work at a lab that's cutting edge like what you're doing?
So what I look for in students isn't so much grades. Grades are important. I'm interested in possible math.
Hey,
The math skills. Yeah.
Could you back up a little bit? We just lost the audio there. Go back to what you said
Oh,
you were looking
sure.
for in a student.
Yeah, so what I'm looking for in students is a student with a really solid math background. That's really important. Some computational skills is really good. Most of my students now are coming with a little bit of Python or a little bit of C, but Python in particular is something that is really quite useful. And I would say the willingness to explore. And not to just simply do something by rote. That's a skill that's really, really important. I want my students to come to me and say, "Hey, I was working on this experiment, and you told me to take this set of 50 measurements and do whatever, but I got halfway through." And I saw something that was weird, and I decided to go off and explore this. I love that. I absolutely want my students to challenge and to explore different ideas, because that's the sort of thing that is the hallmark of a scientist. So learn math. Oh, and one other thing you probably wouldn't expect me to say, but I always tell every student, take writing classes.
Amen.
I know you're going, writing more English? Really? Why would I do that? Bless you. Because I spent so much of my time writing, more time than I really like to, but all those writing classes I took as an undergrad actually paid off tremendously. When you think about it, I had to ask somebody in a 15-page document to give me $2.5 million to build a magnet to float dirt inside of it. You got to be able to write pretty convincingly for somebody to do that. So take those writing classes.
Fantastic. Do we have any other questions for our seminar speaker? We great? Well, let's give our seminar speaker another round of applause.
Thank you very much.
Thank you. Your enthusiasm is infectious. So, wish I could go back and be a grad student.
No, you don't. Nobody ever says that. Thank you all very much. I appreciate it.
All right, absolutely. I appreciate your time. I'll send you an email tomorrow and kind of wrap up with you.
Okay, great. No
all right.
problem, bro.
Thank you very much.
Thank you.
Bye-bye. All right, bye-bye.
Awesome. Good night.